Okay, here we go. This is hopefully the last entry in our breathtaking serial on chaotic motion of the damped-driven pendulum. And so we left last time thinking that maybe there was a nice, kind of pleasing on the eye and easy on the brain graphical way of representing or of seeing the relation between our driving force and our displacement phi of our pendulum, or if there, more importantly, if there's a way we can display it graphically that would give us more insight into the richness of chaotic motion in this system. And one of the ways of doing that is with a bifurcation diagram. And we're going to go through the process of how those are made now. So the first thing we need to do is decide on a range of values of gamma that we want to display. And this works for, in our case, gamma is our ratio of our driving force over the force of gravity on our pendulum. But I mean, again, in any other system, this could be voltage, or this could be something else. This is just what it is in our case. And then we want to choose a large number of values within this range that we want to display. So say we're evaluating gamma from 1 to 2 and we pick 1,000 values within that range. So we're going to be evaluating phi at gamma of 2.0000 and gamma and 2 and 1/1000th and gamma of 2 and 2/1000th, so on until gamma of 3. And then we want to numerically solve the equations of motion for each value of gamma from t naught to of t max so that all of the transient effects are long since passed. And so after we do that, what we're going to get is, let's say we chose 1,000 gammas, we're going to get 1,000 of these graphs here. And then this is where it gets a little bit tricky, and I sometimes get confused here. And what we want to do now is evaluate phi, find a value of phi at each one of these graphs for a certain time in a given time interval. So we want to pick a time interval at the beginning of which ti, from a ti to a tf, time initial to a time final, and we want to pick a TI such that the transient effects have long since passed, and a TF far away enough from the TI that we can get a good picture of what's going on. So say we choose 30 in this case for gamma equals 1.06, we choose from 30 to 40. I mean, it's periodic motion, it should be enough. So we find the value of phi at t equals 30, and it looks roughly like negative 2.1. And then our next one, at t at 31, it looks again like it's negative 31, or negative 2.1, sorry. And we do this for all of them, and we're going to end up that our 100 points that we're evaluating, or our 10 points in this case, that we're evaluating phi at are all going to be equal to the same thing. They're all going to be equal to negative 2.1. And for actual bifurcation diagram, we're going to pick a big number. So say we pick 100 and evaluate all these points from t equals 30 to t equals 130. All these points are going to be equal, all these phi values are going to be equal to negative 2.1 because that's the definition of periodic motion. The same values repeated periodically at a set interval. So now we're going to move on to this solution. And we're going to do the exact same thing. So we're going to evaluate the value of phi at t equals 30. And it looks like from the graph it's roughly negative 1.8. And now we're going to evaluate at 31, and it looks like it's roughly negative 2.5. So these are two different values. But now it alternates between these two values all the way into infinity. So say we pick 100 points again and do this from t equals 30 to t equals 130. Half those points are going to be equal to negative 1.8, and half those points are going to be equal to negative 2.5. And we do that again for each one of these equations where the parameter is set, or variable parameter is set at 1.081, 1.08, whatever, for each interval that we set between the range that we want to examine the relationship between gamma and phi for. And when we do that, we end up with a bifurcation diagram. And so this one's from the John Taylor textbook again, and it's evaluated the range from 1.06 to almost 2.0. range of 1.06 to 1.087. And in this case, he's chosen 271 intervals of gamma, or 271 intervals of gamma in this range, equally spaced. And so he's evaluated the equation of motion we had for the damped-driven pendulum 271 times for that value of gamma, and he came up with 271 of these equations. And then he picked a TI of 500 and a TI or TF of 600, and did exactly what we did here from t equals 500 to t equals 600. And for every interval, he took the value of phi and made that a point. And so so basically you can imagine each vertical line consisting of 100 points. And because at this point where gamma equals 1.065 something, 4 something, because it's period 1 and all those points land on the same value, all those points conglomerate around a single value of phi, sorry. And so as gamma increases, this value slowly decreases until it gets to a certain critical point, which is our first bifurcation point. And then we can go back to our other previous graph and see now there's two values of phi for every consecutive value of t. And we can see this in a graph because there are now two values of phi for every consecutive value of t. So there's still 100 points, but 50 of these points are piled on top of each other at each one of these points, at each one of these points, because there's only 2 points, but 50 points go into each one of these points. And this continues until we hit our next bifurcation point at gamma 2, wherever we hit period 4, right here. And again, we have four different values of phi that t alternates in between as t progresses into infinity. And this is again represented here by these four different spots consisting of 25 points each. And then we hit more and more bifurcation points until eventually we hit, at this threshold, we hit pure chaos. And here we can really get a better sense of the distribution of the points, as every single point has a unique position. So there's 100 points along each one of these lines, each at a different position. And that's how you make a bifurcation diagram. And these get really interesting as they get more and more complicated. And already you can see why we had to pick such a simple system to analyze, because making this diagram alone took 30,000 calculations. I mean, there's 30,000 individual points on this diagram, albeit, given some of them are on top of each other, but altogether there's 30,000 different points of data. And this is for a very simple system over a very short or a very small range of parameters. And as soon as you get into bigger, more complicated systems, this easily goes into millions and trillions of calculations, and you can see why nobody can ever predict the weather beyond a couple days. And so this is a similar bifurcation diagram, except this time it's angular velocity instead of angular position, and it's for a longer range of motion, or longer values of gamma. And this here is kind of zooming out of what we were looking at earlier. And this section A is what the graph that we were just looking at is zoomed out. And then this section B is a section of pure chaos. And then this section C here is another region of stability, which is very interesting, and it really shows the rich, not predictable, but the patterns that emerge within chaotic systems, because here we have 3 stable states here that's alternating of period 3, and then we have another section of chaos, and then we have another stable state followed by another periodic cascade until we get to finally another region of instability. And this is very interesting because even though it's a chaotic system, there emerge from its chaotic behavior periods of stability, such as this one. And the original one we had earlier for stronger and stronger driving forces. I mean, this is a very large period of stability in the behavior of a damp-driven pendulum. And so this, I mean, this can be expanded to giant systems. I mean, this is example that came to mind is the big red spot on Jupiter. Um, I mean, Jupiter is a big, giant mess of fluid mechanics, but yet there are these patterns that emerge in its, I mean, giant chaotic system of storms. And I mean, the big red spot's been stable for thousands and thousands and thousands of years. And if we go back to the bifurcation diagram, although this is a huge simplification, that's represented by, this stable state here, for example. Although, I mean, again, a very huge simplification, but it just goes to show that there is a predictable nature to chaos, and then systems that we ignore and write off as being nonlinear and unanalyzable and completely chaotic do have qualities about them that we can measure and we can learn about, which is, I guess, one of the more intriguing points of the study of chaos. And I'm going to end this presentation here because it has already gone on for far too long. And I hope everybody on the other side listening to this is still alive and hasn't died of boredom. And I tried to explain a complicated and chaotic topic in a very complicated and chaotic way. And yeah, anyway, bye.